Hi, I want to talk about the method of deriving the kinematic equations making use of calculus. And it's part of where we get a little bit of some of the unfortunate terminology that you see used in physics books that can lead you into thinking that one equation or another equation is a little bit more important than the others. So, kinematics is all about the study of motion for motion's sake. And typically in introductory physics, we focus on three properties of kinematics. Location, where an object is as a function of time. So we'll use a vector x as a function of t. Velocity, which is how our location is changing in time, and we use a symbol vector v as a function of t. And finally, acceleration, which we'll use vector a as a function of time. And acceleration is how the velocity itself is changing. Or, to put it in another way, if the same change that you're seeing now were to keep happening forever, what is the motion eventually going to be doing? Now, if we go beyond, there are additional kinematic principles and properties. There's a kinematic property known as the jerk, not the Steve Martin movie, but it's related to how the acceleration is changing with respect to time, and you could even look at a changing jerk. We're not going to do that in this class. We're only going to do one homework example, taking a look at the idea of having a changing acceleration. But if we wanted to derive kinematic equations, if we start with the location of an object as a function of time, we know the whole story of that object's motion. Everything there is to know about it is contained in that function. Because velocity, I said, is the change in location with respect to time. Mathematically, that's the derivative. The derivative answers the question, how much does our function change with respect to our variable? So for acceleration, acceleration is the derivative of the velocity function. So that means acceleration is the second derivative of our location. And if you did want to take a look at calculating the jerk, well, the jerk would be the derivative of acceleration with respect to time, which means it would be a second derivative of velocity with respect to time, which means it would be a third derivative of location with respect to time. But we're not going to look into that piece very much at all. Now, we could derive kinematic equations for the case of dealing with a constant acceleration by making use of the opposite of derivatives, antiderivatives, or integrals. So, with a constant acceleration, we start with the assumption that if we take the derivative of the acceleration, we get nothing. There's no jerk. Zero. So if I integrate both sides of this equation, I would get an acceleration, and the integral of zero is going to be a constant, because the derivative of any constant is zero. And that constant is going to be what we call our constant acceleration in the direction we're looking at. So for this example, I just chose the x direction, I hat, just because it's a good direction. Now, to calculate velocity from that, well, here I have a constant. So if the derivative of my velocity with respect to time is equal to that acceleration that I have, I can multiply both sides by dt, and if I integrate the left, integrating the left would give me my velocity. Integrating the right-hand side of that equation is integrating acceleration with respect to time. So I have a constant times the integral of dt in the same direction that I'm dealing with. So a constant I can just pull out of my integral, and the integral of dt is just going to be my time t. But if we're dealing with indefinite integrals, that means that we would also have to add in a constant of integration. And in physics, rather than using C or big C as a generic constant like we do a lot in math, usually we'll say our constant of integration is going to be the starting conditions, what our velocity would be at the initial moment. So my velocity then at some time t later would be my acceleration times time plus my initial velocity. And this would be a constant that I would have to pull some sort of information in order to know or in order to identify, right? Because if we're just given that we have an acceleration, we can't know a single unique constant without other pieces of information to go from. Well, finally, if we wanted to take that velocity equation and get the position equation, again, I can integrate it. So dx dt is my velocity, or the integral of dx would be the integral of my velocity with respect to time. So I have a constant, my initial velocity, that becomes my initial velocity times time. I have at dt. Well, when I integrate t with respect to t, I do the reverse power rule. I'd have to multiply by 1/2 to account for the 2 that would be brought down in a derivative. So I get 1/2 times my acceleration times time squared in the x direction. And then we'd need our new constant of integration, so we could call it our initial position, x sub I. So, about that unfortunate language. Physics textbooks like to call this the primary velocity equation, and this the primary displacement equation. And there's nothing primary about it. The only reason why they're called primary is that they're the first equations you get integrating backwards from this starting point of the derivative of acceleration is equal to 0. So if you're following through an algebraic method of trying to identify the 5 possible variables of motion you'd be dealing with, you found your 3 variables that you need, all of those equations that we talk about in the algebraic formulation of constant acceleration kinematics are all primary or secondary or whatever. They are all the same story. It's just, this is telling the story using calculus when you could tell the story just using simple algebra. Thanks for watching.